Hey there. So now let's do the Decay Setup. So already remember, we just need to convert the meshes to Fluent. So what you need to do is just put this, then update, you get the mesh, and then move the meshes. We're going to work outside workbench. Okay, so just convert meshes and then start to move meshes. You don't want to do this. Remember that here you can download the meshes. You already have the meshes, clean meshes, exactly what we did. And then here you will have the settings if you want to do the automatic settings, but we're going to do it from scratch, basic settings. So see that you have the mesh here, look at the location. Okay, so as you go, I have my cases here. So just to show you again, I was working here, I was working in this, DB0, and it's telling me that this mesh is located in sys5. So you just copy that one and put it anywhere, okay, outside of this directory. In my case, I move it here, this my Fluent, and see that we have the 2D and 3D meshes with the setting. Okay, so we're going to work here. Okay, so now that you have done this, you can close this one safely after converting the meshes. Also, just to point out, remember I mentioned that you can generate meshes also using Fluent. This is this tool here that you have here. However, this tool works only in 3D. Okay, you need to have a 3D mesh. I'm not going to address this one. You can generate nice meshes also here, but for our purposes, I think ansys mesher works really well. Okay, but if you are interested in this one, just let me know. I can show you a little bit, but it's not the scope of this course. Okay, so let me erase that one, save, and I can safely close here. And now I'm working in Fluent. Okay, so here I already opened one case just to show you. We're going to do first the case setup. So there are a few videos now. So first only the case setup, then running the simulation because it's a little bit time consuming, and then we have the post-processing also that is a little bit time consuming because it is unsteady. Okay, so here see that I already have the case setup. This is reading the setting files. Okay, so see that pretty much everything is the same. Okay, what is important, as I mentioned, that when reading this mesh, let me plot it here. See that it's a fully 3D mesh. You have these two faces here. So in my case, I group these two faces in a single patch. Okay, so in this case that I have here, so it might be better to have front and back. Nothing changed. Okay, it's exactly the same. So see that as you have this, also you can create a plane, and see that now you have the MIG plane, and you can do all your post processing there. So what is important about this case, when you set boundary conditions, this patch, the yellow one that you see there, you need to put it as symmetry. Okay, and when you put it as symmetry, it will automatically work in 2D. So see that in this case, we're putting many monitors. We're creating also many monitors here. Okay, so we're going to explore this. Okay, and let me minimize here and let me move here. Okay, so see that I'm outside Fluent. I want to work in this directory. So you do this only. Okay, you need to give this working directory only when you are working in a standalone Fluent. If you are working in the workbench, it automatically will know how your files are linked. Okay, so see here that you have dimensions. This is the 3D. Okay, put 3D, double precision, choose your number of processors. I will use 4 and nothing else. Okay, start. So I'm going to read the mesh and then I will start to do the setup. So I will choose a Reynolds of 1000, okay, for my setup. The same way you have the setting there, so once you read the mesh and then just read the settings, and you will have the full case setup there. So we are there, read mesh, read this mesh. Okay, so I read my mesh, and now you can do the case setup. So usually always you can go here in graphics and you can plot your domain and everything. Okay, so see that this is what I have. Okay, so in my case, remember that I didn't do the separation front and back. So see that this patch is grouping these two there. That is not a problem. Okay, it's up to you if you want to leave it like that. But it's still what is important, that it's always a 2D mesh. So usually here, remember scale to know your dimensions. So my dimensions are okay. Mesh quality, Mesh quality is perfect. And if you want to know the dimensions, you have here some statistics. So everything seems to be okay. So I think we can move to the next step, to the case setup, so that you have that. So I'm going to show you a basic case setup now, or I'm not going to show you all these options here that you have here. Just reopen this case or do the setting to see everything, but we have explored that. So see that in general, the new modification that you need to do here is here. Now this is a transient, so now you have the time derivative. The rest exactly the same. Okay, you go here, viscous models, you want to enable energy. It's exactly the same as we have done previously. Okay, so for the moment it's compressible. Fluid materials, let me go to air, and let's say that I'm going to do this, and my viscosity here needs to be that for a target. Let me confirm here what value I was using here. So yeah, see, I was using 1000. So I put this one, the inlet velocity is 1. I know that the diameter is 1, so my Reynolds will be 1000 on a steady regime, and it's already turbulent. Okay. Then cell here. So here you go here, and if you have different materials, you will need to apply the material to that region. In this case, only one material, so it's okay, nothing to do. Then important boundary conditions. So here's where we start to select the boundary condition. So see that the bottom wall, as you recall, okay, your bottom wall is this one. Okay, so that one for us, I want to slip there, which is a symmetry. Okay, so you have two options to have the slip boundary condition there. You can put symmetry, but remember that symmetry will work if you have only planar faces. Okay, or you can put it a wall here. And when you enter into the walls options, here you can specify shear. So if you put shears to 0, it's lit. Okay, so it's up to you. Okay, so in this case, I will do it like this. I will put top also like this. Okay, and then these two that represents this and this, I will put their symmetry. Okay. So usually those are planar always. Okay, and then the inlet, velocity inlet. Let me put here velocity normal to boundary 1. I will use default parameters. Then outlet, pressure outlet, okay. 0, 1, okay, these values are okay. So let's see that you have your case setup here. Button, so let's confirm that everything is okay. 0, 0, 0. Cylinder is a wall, okay, and it's a wall with no slip. You have there, okay. Inlet, velocity inlet, okay, this is interior, nothing to do there. Pressure outlet, top. Let's check that the top is specified, and then see here that you have the symmetry there. So those two patches. So if you want to confirm that what are those patches, just go here. See that you have. Okay, you set up your boundary conditions, then you move nothing to do here, nothing to do here. Reference values, you are going to compute coefficients, just give it here. So I want to use freestream values from the inlet. I know that my frontal area, so in this case, see that your frontal area. So this is why it's a good idea to have this extrusion 1, okay, because always multiply by 1. So if you put there a different value, you need to put the right. So if, for instance, if I had done that extrusion using 2, here my frontal area will be 2. So it's 1 diameter, 1 this, okay? So be careful with that. And your velocity values, everything okay. Nothing to do here, nothing to do here. Methods. So now things change a little bit here. So now that we're running on a steady, see that now you have access to time derivative in your equations. And see that now the default proposed by Fluent is different, okay? It does not propose couple. Couple is a very good method, but for on a steady cases, it's very expensive. So I don't recommend you to use it because it will take much longer than other methods that are specifically not that works better on a steady. So I recommend you to use Piso, okay, this one, and take the default options, okay? So be careful, you can use couple, but later you can do these experiments and check the cost per iteration or the total cost of the simulation. You will see that this is much heavier, use much memory, and takes more time. So the piezo, it is okay. So let me confirm what setup do I have here. So actually piezo, and I have this one. So see that you have piezo, least square, second order, everything second order. And here also you have for your time derivative, you can also choose the order of accuracy. So you can go first order, second order, or bounded second order. So the idea here is the same. If you use a first order method, it is dissipative. However, time dissipation is not as severe as the dissipation that you add in the momentum or energy equation as you use first order. So you can do this, okay, if you are using small time steps or CFL numbers less than 5. Okay, but for our purposes, let's go here, second order implicit. Okay, let me choose there, second order implicit method. Controls, nothing to do here. And now your monitors. So you have a series of default monitors, but now you need to add more monitors, okay? So let's add one very important. Remember I mentioned the CFL number. So if you go here, new, you go volume, okay? In this case, it's volume because we have this one. If you were doing this one in a 2D, it will be surface. Okay, so volume, and I want to know the maximum CFL number, okay? So I will call it max CFL, and usually the CFL you will see it in velocity, and select here cell convective current number. Okay, so every cell will have different CFL number. So here it will take in your whole domain, select your whole domain. This is your whole domain, and it will show you the maximum value. So I want to report to a plot, and okay. So you have that monitor, and then you can add the traditional monitors. Okay, so you see that in the case, that predefined case, there are many monitors. Let me revisit this here. So see that we okay, you have imbalance, average Y plus, CD, CL, you have all those monitors, okay? I'm not going into details for all those monitors. Let me add, for instance, I want to add the Y plus, okay? Y plus is a surface, okay? And I want the average. Select the surface, cylinder surface, and you want turbulence, and then you want wall Y plus. Okay, so you call it here Y plus average, report to plot, and you are okay. So you can plot also imbalance and everything. So we're done here. Okay, these are my basic monitors. My residuals are okay. I don't want to put any convergence condition, but if you want, you can put it. Then let me go here, initialization. Okay, so here I'm going to initialize using the freestream values from the inlet. Okay, and at this point we should have initial conditions. Okay, so here you can plot and see that basically we're not going to see anything, okay, because we put everything 0. But what is interesting here, just to show you that after you initialize your solution, you will have access here to these results that you can, for instance, create surfaces. So let me create a new plane, and it will be that one, create. So see that this is my mid plane, you have it there. And now I would like to visualize everything in that mid plane. So instead of putting those two walls, okay, so you will see your solution there. Okay, and now let me add a point to monitor the solution. Okay, so I will add a point. Okay, and you put here the coordinates. So I know I will put it in 4, 0, 0. Okay, so this point can be inside your domain, so or it can be in a wall. So I know that my C maximum is 1, so you can put it also in that wall. Okay, there is no problem. So usually I like to put it in the midpoint, you know that. Okay, so you put it there, and you have your point. So in this point, you can monitor whatever you want. Okay, so you can create also lines. We have seen that. Okay, it's up to you. So these are the basic ones. Remember, you go to the predefined case and see that I put all these monitors. Okay, so now that we have this, okay, see that we have the decay setup. Okay, we have everything. Okay, we need to do a little bit more, but let's run a couple of iterations. So see that now the difference, this is a little bit different from previous, that we were running instead, you just give the maximum number of iterations. Here, in theory, there is no maximum number of iterations. You let it run for long times, okay? So see that here you define your time step, and usually you as a user, you have an idea of this time step, okay? So I know that, for instance, you can go here and put something like this, and a small time step, okay? But you need to let it run a little bit. Remember that you need to monitor the CFL number. So let's say that I want to target a CFL number, something about 1. So this is what you do. It's something kind of iterative, okay? So you put there a value, monitor your CFL number, let run your simulation, and you see that, okay, if it is too low, you can increase a little bit. If it is a little bit too high, you can decrease a little bit. Okay, then here also you put the number of times. Okay, you will put here, I know, usually put a large value. So this number of times this will give you the total time of this simulation. Okay, so it's up to you to run this one for 1 second, 10 seconds, 100 seconds, 1,000 seconds. Okay, so let's run this one. So the method that we're using also, it is a iterative method, okay? So while it's doing one time step, it's also converging. So this is the maximum number of iteration per time step. Okay, so let me run a little bit just to show you what is happening, okay? So still we need to set up something, but if I press calculate, see that now you have time. See that at the beginning, it is iterating to the maximum number, but then slowly, see that now it's reducing the number of iterations, okay? So see that here you have y plus value, see that CFL is relatively low, okay? So still we can increase our time step. So you leave it like this, and if you want to run 100 seconds, you will need to run this one like 100,000, 100,000 iterations. So that is a lot, okay? So see that you have a relatively small, then we put here a stop here. So see that you can stop here. Stop at the end of the time step. Didn't stop. Let me now force it here. So see what is happening is that it is converging. Each time step is converging in one, basically in one iteration, okay, of this one. This is what we want. We want a fast convergence, but this still we can increase the time step. So ideally, an advice here that when you run, ideally, you should converge in no more than 10 iterations here, okay? So that is a good standard practice. So let's see, look at that. You have this CFL number, and also we have a solution. We can post-process here. So see that you have your solution. You can access all your fields and everything. So just to show you here, let's increase the CFL, the time step. So now I will put 0.5, okay? See that I stop it, and you can keep computing with no problem, okay? So it will start from the previous solution. So see that now you have a jump here in residuals, but don't pay attention to this, okay? This is not a direct indication. You need to monitor forces. But see that with a time step of 0.005, see that now your CFL goes to something about 0.5. And see that here is converging in 4 iterations. So see that from this to this, and see that basically you are accelerating your convergence by a factor of 5. Okay, so this is what is important. We want to go with large time step because we want to converge to get to the final time that we are aiming fast. Okay, so see that still I can increase my CFL number. So let me stop it. Okay, now this one, it's not stopping. Sometimes happens that it does not stop. See, if it doesn't stop, go to the text user interface and press Ctrl+C, and that would kill that iteration. So we can go here, and now let me double. So now we are going even larger in time step, okay? So let's say that, let me do 20 time step, okay? So if I press there, see that user, you have always your jump there. See that jump here in the CFL, and now see we are about that target CFL. So see that it arrived to 20 time step and stop. And see that this is what we're aiming, okay? So let's say that this is our ideal time step, and see that it's converging in 4 iterations, or 3, better 3. So this is the ideal, okay? So your ideal time step is the one that it will give you a convergence in every time step that in no more than, let's say, 10 iterations, ideally 5 iterations. So for instance, see that if I go here, increase to 0.5, see that my CFL number is much larger, I will converge much faster, but see that now it's taking about 14 iterations to converge. Still, this is good, this is okay, but something ideal that it will give you a good compromise now between computing time. Okay, it's a stop here. That it's something that it will give you, a good report between the computing time and number of iterations. It's something that it will converge about 5 iterations here. Okay, so let's put here, let me leave it here to 0.1, and at this point, see that we found our time step. Okay, so I can leave it like this, and now we can run the simulation up to, let's say, like we have here. See that here I run this case up to 100. So see that you're monitoring that. So let's keep doing Decay Setup. Okay, so you have your monitors, everything. Okay, and now something interesting to do, because it's also important to visualize your solution, what you are running. Okay, so you have access also to animation controls. So as you go here, calculation activities, see that you have solution animation. So by the way, this is only available after you initialize your solution or you run your solution. Okay, so here, let me go here, and let me put it like this. Okay, this one is okay. And let me create a new one where I want to have, see that you still you're starting to see there the vortex creating. And let me put in another one displaying, let me put there velocity. Okay, and see that I want to do solution animation here, calculation activity, solution animation, new, and I want to animate what? Okay, I want to animate, so see that you access here these objects that you haven't resolved. So this is why you need to initialize or run a couple of times. So you see what you want to animate. So I want to animate contour 1. It's going to say, so here you can save the type of file. So you can save everything in memory, you can save in this default format that I propose, HSF, I guess it's proprietary from Fluent, or you can save it in JPEG file, it's up to you. So for instance, let me check here that I want to save in JPEG files. Here you give a location, usually here I prefer just to, instead of putting that there, I prefer to go like this. Important also here, you need to see animation view. How do you want to see this one? So usually use active, put this one is the view that you are selecting there. So you create one animation object, and let me create another animation object that correspond to contour 2, this one, use active. Okay, correspond to the active view that you have there. Okay, that what you are seeing there. Okay, and what is important here is you go back here, see that you can see that show me this every time step or every top iteration, whatever. So usually I will say here, I want to see that every 0.5 seconds, show me that. Okay, so it will save that information in disk, but also it will update this view and you can see the evolution. Okay, and let me go here, flow time 0.5. Okay, so in this case, I'm saving JPEG. In this case, I'm saving the HSF file. I will show you the difference, okay? So now that I set up this monitor, you can go, let me go and set up, for instance, a report for forces. So let me go here, force report. Let me do it just for drag. I have my cylinder. Okay, drag coefficient. I will call it CD and report to plot. You can report to a file also, so let me check that one, and everything is okay. You have it there, okay? And if I go back, so just go to this one and see all the options, okay? I'm not going to visit that, but see that all these monitors that I put there, your report plots, everything. And see here that I created these animation monitors. And something interesting that see here that in these points, I create a report. So see in those points, I'm plotting the velocity. So see that I'm selecting all and just sample the velocity, this component. So here it doesn't matter if you select phase minimum, maximum, or point minimum, maximum. Okay, I usually put this one because it's just getting the puntual value, okay, in that point location. Okay, so see that you can sample in whatever. So you're putting all this information on all these points. Okay, saving that information. Okay, so for instance, let me do it also as well. Okay, here. So let me create that monitor. So if I go here, new, will be surface, I will put, I know, phase average, it doesn't make a difference. And I want to sample in this point, and I want to sample velocity, and I want to sample this Y component. Okay, I will call it 0.7 by and report to plot. Okay, so everything that is passing in that point, so let me go back to the mesh here. So I have my mesh here, point and this plane. So let me hide the plane. So everything there, you have the plane. So everything that is passing the point that is passing through okay, here, everything that is passing through this point, it will be sampled. So in this case, I didn't put it in the middle. I put it just in this phase. Doesn't matter, it will sample the same. Okay. And this is also, let me press calculate again. Okay, let me run now for 50 iterations. And see that it's starting all the monitors. So see, this is the point monitor. So this one is now accumulating all the information of the velocity passing through that point. So basically, this is important. Later, you're going to see we're going to do more advanced post-processing for scale resolving to compute now to do the plot of the energy spectrum. You need to put all those probes there, and then you need to gather the information of velocity fluctuation, or if you have that, you can add it, get the information of the turbulent kinetic energy. Okay, so basically in those points you put it there and you're just accumulating information. Okay, so see what we have here. Now you have your residuals, your maximum CFS, something about 1. See that this is the average Y plus value. Here the CD that we added, then the velocity monitor there. And see here that now we have here the velocity and pressure contours. And let me show you, let me run for a longer time here to show you this one. That now this one is updating automatically while you are running. So see that every 0.5 seconds it will update. Okay, and it will show you the flow evolution while it's running. So this is very important to see that it's updating. And if you go in the directory that you are working, you should have the files here. So see that you have this file, that this is the Fluent format, or you can have also this JPEG file. Okay, so see that there you see so this is very important. While you're running, you can add, so you need to create your contours. You can do it with vectors, whatever. Okay, you add that in animation. And see that here, it's not only looking at these quantities, it's also important to look at the color, because also the colors is giving you some information that is not contained in those quantities. So see that you have all the evolution here, and see that here is converging into iteration. So when you see this one that is converging into iteration, or basically in 1, this is also an indication that you can increase, you still can increase your CFL number. So as you go here, your time step, let me increase it to 0.02, and see that the number changes, but slowly will. So probably this will be the ideal time step, 5 iterations here. But now you get an idea now. So to get 100 seconds in this case, you will need to run like 5,000 time steps. So remember, this mesh is small, so you see that the cost is low, but when you start to work larger meshes, things become expensive, okay? So this is it. This is the basic case setup. See that this monitor here, we start to see now the velocity fluctuations. Okay, so let me stop here because I wanted to show you why I prefer this 3D mesh for post-processing. So if I go here now, new, and I want to post-process in the cylinder wall, see that now this is a surface, so it's easier to see, for instance, the Y plus value. So remember previously in that line it's difficult. So see that now you have this one. So this is just basically this. This is why I prefer to post-process, to run the cases, the 2D cases like this, because it's easier the post-processing. But theoretically your solutions will be the same, okay? Your case setup is exactly the same. I will show you later that. So at this point, we have everything here. So I will stop here. Okay, just to end here. So as you are running and you have these solutions, here, see here that in results, you have animation also. So whatever you are saving here, you can animate it here. So you go playback and see that as you press play, you can see the animation, okay? And then here you have to write, you can write the movie and everything. So you add here the solution animation control, and then as it gathering information, you can save, you can play everything here, okay? So we already visit the scene here, and now we're in the playback control. So you can save this one to the case. You have your case running, and then if you close Fluent and then reopen it tomorrow, all this information is saved, okay? Everything that you have there is saved. So this is how we run on a steady case. So as you see, it's a little bit trickier because you need to monitor now the time and and control many scenes, but the idea is the same. So at this point, let me stop here, and now in the next video we're going to go and run this case. So basically I will use a predefined setup. Okay, I will read the mesh and and then the settings as a case predefined with all monitors, and I will launch it, and let's see how long does it take. Also, I will show you how to compute the steady statistic that we didn't do here. Okay, so that's all for this video. See you next time. Bye.